The warning would come without hesitation. No declaration, no confirmation, no second chance. A signal, just a signal, racing across continents at the speed of light, telling commanders that somewhere beyond the horizon, nuclear missiles might already be in the air. And in that moment, the world would have minutes. Minutes to decide, minutes to respond, minutes to determine whether civilization would continue or end. This was the terrifying reality of the Cold War, not a distant possibility, but a constant condition, a fragile balance where a single misinterpretation, a single false alarm, or a delayed response could trigger a chain of events no one could stop. Because once a nuclear missile is launched, there is no recall. There is only impact. And for decades, that reality shaped every decision made inside the most secure command centers in the United States. Deep underground, behind reinforced doors and guarded by layers of secrecy, military officers monitored the skies with relentless precision, watching for signs that the unthinkable had begun. But there was a problem that haunted strategists, engineers, and commanders alike. Detection was not enough. Even if the United States could see a launch the moment it happened, even if radar systems tracked every trajectory with perfect accuracy, the outcome remained the same. There was nothing to stop it. No shield, no interception, no way to reach into the sky and change the course of what had already been set in motion. The entire doctrine of nuclear deterrence rested on retaliation, not protection. The idea was simple and brutally effective. If one side launched, the other would respond with equal or greater force. Mutual destruction, guaranteed. But that logic came with a dangerous flaw. It accepted that millions would die, as long as both sides lost equally. And for a nation that had built its strength on innovation, precision, and control, that wasn't enough. Because the real question was never just how to respond to a nuclear attack. It was whether it could be stopped at all. As tensions between the United States and the Soviet Union escalated, both sides raced to develop more advanced delivery systems. Intercontinental ballistic missiles grew faster, more accurate, and more numerous. Submarine-launched missiles added unpredictability, hiding beneath the oceans where detection became even more difficult. The timeline of war began to shrink. What once took hours could now happen in minutes. And that compression of time created a new kind of pressure, one that pushed human decision-making to its limits. There would be no room for hesitation, no margin for doubt, which meant that the systems designed to detect and respond to these threats had to operate with absolute clarity and absolute speed. But clarity was not always guaranteed. Radar systems could be deceived by atmospheric conditions. Early warning networks could misinterpret signals. Even reflections of sunlight off high-altitude clouds had, at times, triggered alarms that appeared indistinguishable from real missile launches. And in those moments, the difference between false alarm and global catastrophe rested in the hands of a few individuals, forced to make decisions under unimaginable pressure. The danger wasn't just attack, it was uncertainty. Because in a world where both sides possessed the capability to destroy each other, the greatest threat was no longer the weapon itself, but the possibility of misunderstanding it. That realization began to shift the way American strategists thought about nuclear defense. Retaliation alone was no longer sufficient. What was needed was something far more ambitious, something that could change the equation entirely. A system that didn't just detect missiles, but could stop them, intercept them, neutralize the threat before it reached its target. It was an idea that, at first, seemed almost impossible. Intercepting an object traveling faster than the speed of sound, across vast distances at extreme altitudes, within a narrow window of time, require a level of precision and coordination that pushed the limits of existing technology. But during the Cold War, limits were not accepted, they were challenged. And as American engineers, scientists, and military planners began to explore this concept, they weren't just building a new weapon, they were attempting to build something that had never truly existed before. A defensive shield in a world defined by offensive power. A system capable of reaching into the most dangerous phase of conflict and altering its outcome. If you're interested in Cold War stories where technology reshaped the balance of power in ways most people never saw, consider subscribing. Because what came next would redefine what defense really meant. Because once the idea took hold, it couldn't be ignored, and the race to stop nuclear war had already begun. The concept was as bold as it was controversial. Instead of accepting that a nuclear attack could only be answered with another, American planners began to imagine something entirely different. A way to intercept a missile in flight, to destroy it before it ever reached its target, to turn the sky itself into a defensive barrier. It sounded almost impossible, because the challenge wasn't just technological, it was physical. An intercontinental ballistic missile doesn't move like a conventional aircraft. It doesn't follow predictable paths within the atmosphere. It launches with immense force, exits into space, and then re-enters at speeds that push beyond comprehension. Faster than anything most systems of time were ever designed to track, let alone stop. To intercept it, you wouldn't just need speed. You would need precision, perfect timing, and a network capable of seeing everything, everywhere, all at once. The United States began assembling that network piece by piece. Radar installations expanded across remote regions, positioned to detect launches from thousands of miles away. These weren't simple tracking stations. They were part of a growing web of early warning systems, designed to identify threats the moment they appeared. At the same time, advancements in computing began to change what was possible. Massive, room-sized computers, primitive by modern standards, were now being tasked with something unprecedented, calculating the trajectory of a nuclear missile in real time and predicting exactly where it would be at any given moment. Because to intercept a missile, you don't chase it. You meet it at precisely the right point in space, at precisely the right second. And that required a level of coordination that had never been attempted before. Out of this effort came one of the earliest and most ambitious missile defense programs. Systems designed not just to track incoming warheads, but to launch interceptors capable of destroying them mid-flight. These interceptors were not conventional weapons. They were built for a singular purpose: to reach extreme altitudes at incredible speeds and collide with or detonate near a target moving faster than sound, faster than reason, faster than reaction. The margin for error was almost non-existent, a fraction of a second too early, and the interceptor would miss, a fraction too late, and the warhead would already be descending toward its target. Everything had to work perfectly, and yet perfection was not guaranteed. Tests revealed just how complex the challenge truly was. Tracking systems had to distinguish between actual warheads and decoys, objects intentionally designed to confuse radar and overwhelm defenses. Even small errors in calculation could lead to complete failure. But failure didn't stop the program. It refined it. Each test, each simulation, each near miss provided data that engineers used to improve guidance systems, enhance radar resolution, and reduce response time. Slowly, the impossible began to look achievable. And as these systems evolved, they started to take on a new role, not just as a defensive measure, but as a strategic signal. Because if one side could intercept incoming missiles, even partially, it changed the balance. It introduced uncertainty into the equation of attack. No longer could an adversary assume that every missile would reach its target. No longer could the outcome be predicted with absolute certainty. And in the Cold War, uncertainty was power. It forced hesitation. It created doubt. It made even the most aggressive strategies more complex, more risky, and ultimately less appealing. At the center of this shift was a growing realization inside the United States military. Defense was no longer passive. It could be active. It could shape decisions before a conflict even began. But turning that idea into reality required more than theory. It required a moment, a real scenario, a real test, where everything would be put to the limit, because until a system proves itself under pressure, it remains just an idea. And in the high-stakes environment of the Cold War, ideas weren't enough. Only results mattered. And soon, the system would face a moment where results were all that stood between control and catastrophe. That moment didn't arrive with fanfare. There were no headlines, no public warnings, just a signal. Inside a U.S. early warning facility, deep within a network built to detect the first signs of nuclear attack, operators watched as data began to form a pattern that was impossible to ignore. A launch signature, a trajectory, the kind of profile that in another context would have meant one thing, and one thing only. A missile was in the air. In seconds, the information moved through layers of command. Screens updated, calculations refined, The system began to do exactly what it had been designed to do: track, predict, respond. But this was not a theoretical exercise anymore. Every piece of data carried weight. Every calculation mattered. Because if the system failed, even once, the consequences would be irreversible. Across the network, radar arrays locked onto the object, feeding continuous updates into centralized processing systems. The missile's path was calculated in real time, its projected impact zone narrowing with every passing second. And then came the next step, the decision to intercept. This was the moment everything had been built for, the point where technology and judgment converged under pressure. There would be no adjustment after launch, no second attempt. One opportunity, one chance to meet the target in the vast emptiness between Earth and space. The interceptor was prepared, positioned within a hardened launch site, designed to respond without delay. Unlike traditional weapons, this system operated on a different timeline, compressed, immediate, unforgiving. The command was issued, and within seconds, the interceptor ignited. It rose with explosive force, cutting through the atmosphere, guided not by a pilot, but by calculations, thousands of variables processed in fractions of a second. Its trajectory wasn't reactive. It was predictive. It wasn't chasing the missile. It was going to where the missile would be, far above the surface, in a region where the atmosphere thins and the margin for error disappears entirely. The two paths began to converge, one descending at extreme speed, the other ascending with precision. Every system had to perform flawlessly: tracking, guidance, timing. There was no room for drift, no tolerance for delay. As the distance closed, the interceptor adjusted its course, subtle corrections, almost imperceptible but critical. The final approach was not visible to the human eye. It existed in data, in coordinates, in milliseconds. And then, contact. In an instant, the target was neutralized. No impact, no detonation on the ground, no escalation, just a silent confirmation relayed to the network that the system had done what many once believed was impossible. It had intercepted a missile in flight for the operators inside that control room. The significance was immediate. What they had just witnessed was more than a successful test or a contained scenario. It was proof that the trajectory of a nuclear weapon was not untouchable, proof that the sky was no longer an open path to destruction, and most importantly, proof that control could exist even in the most critical phase of conflict. Because until that moment, the final stage of missile's journey had always been inevitable. Now it was something else, something that could be challenged, something that could be stopped, but the true impact of that success wouldn't be measured in that room. It would be measured far beyond it, in the calculations, strategies, and decisions made on both sides of the Cold War. Because once the possibility of interception became real, the rules began to change. From that moment on, the equation of nuclear war was no longer as simple as launch and impact. A new variable had entered the system: doubt. For the first time, planners on the other side had to consider something that had never truly existed before: that a missile, once launched, might not reach its target, that somewhere along its path, it could be tracked, calculated, and stopped. That uncertainty changed everything, because the strength of a nuclear arsenal had always depended on reliability, the assumption that if a decision was made, the outcome would follow with absolute certainty. But now, that certainty was no longer guaranteed. Even a partial defense, imperfect, limited, still evolving, was enough to complicate strategy. It forced new calculations. It introduced hesitation. It made every plan more fragile. And in the Cold War, hesitation could prevent escalation. For the United States, this wasn't just a technological achievement. It was a strategic shift. By developing the ability to intercept incoming threats, American defense moved beyond retaliation and into something more controlled, more deliberate. It added a layer of protection in a system that had long accepted vulnerability as unavoidable. But just as important, it demonstrated something deeper: that innovation could reshape even the most dangerous realities, that the limits of warfare were not fixed, they could be challenged, redefined, and in some cases, overcome. Of course, no system was perfect. Missile defense will continue to evolve, facing new challenges as adversaries develop countermeasures, decoys, multiple warheads, faster delivery systems. The balance would never be static. It would remain a constant competition between offense and defense. But the breakthrough had already done its work. It had changed how both sides thought. It had reduced the sense of inevitability that once defined nuclear conflict. And in doing so, it helped stabilize a world that often stood on the edge of catastrophe. Because the Cold War was never just about weapons. It was about control. Control of information. Control of timing. Control of outcomes in situations where mistakes could not be undone. And in that environment, even the smallest shift toward control could have massive consequences. The system that could reach into the sky and stop a missile didn't just defend territory. It defended time. Time to think. Time to verify. Time to avoid decisions that could never be reversed. And sometimes that time was enough. Enough to prevent escalation. Enough to keep a signal from becoming a launch. Enough to keep the world from crossing a line it could never return from. That's what made this system so significant. Not just what it could destroy, but what it could prevent. Because in the end, the most important victories of the Cold War were not the ones measured in firepower. They were the ones where nothing happened, where a system worked, where a decision was delayed, where a catastrophe was avoided. For more stories like this, where technology and strategy quietly shaped the course of history, make sure to subscribe and support the channel.